Great. Thanks. Can anyone hear me? Good. So I'm Michael Tremmel. I'm stationed here also in Ireland, in Cork. And I just want to plug initially in this talk that we'll be hosting next year's EAS in Cork. So looking forward to maybe welcoming many of you to what is the true capital of Ireland, Cork City. So what I'll be talking about today is the evolution of massive black holes over cosmic time, and specifically what we can learn from simulations. And because of my own expertise, I'll be focusing on large-scale cosmological simulations of massive black holes over time. So the main science objective one of the main science objectives of LISA is to understand the growth of massive black holes. And this plot here is more or less why we care about this, right? Most massive galaxies host a massive black hole in their centers, and the famous M-sigma relation essentially tells us that there's something related to how massive black holes grow and how their host galaxies grow. Somehow, galaxies are regulating the growth of these black holes, and we can see that these black holes are also regulating the growth and evolution of their galaxies by driving massive, powerful outflows that can affect the evolution of entire galaxies. So we care about these things from just because they're interesting black holes, but also we care about them from the galaxy formation perspective. Now, as time has gone on, over the last 10 years in particular, we've gotten really good at seeing smaller black holes in smaller galaxies, different black holes in different evolutionary states, and widening in general our ideas of the underlying black hole population. And this has proven really important because what we've seen looking at the relationship between black hole mass and stellar mass in these observations is that as we broaden our view of the massive black hole population away from just the biggest, brightest black holes that we can see, we begin to see that the relationship is actually much more complicated than maybe we would have originally thought. So if we want to understand the evolution of massive black holes, how they grow, how they affect their galaxies, it's critically important that we get a full sample of the underlying population of these black holes down to low masses. But of course, the black holes in these small galaxies here, these low-mass black holes and low-mass galaxies, should also be interesting to us in and of themselves, right? They represent low redshift analogs to what LISA will be observing at high redshift. But also, we know from cosmological simulations of dwarf galaxies that even these small black holes undergo mergers that will be in the LISA data stream. And these black holes, while they're small, they might not have the richest merger histories. There's a lot of them, because dwarf galaxies are very common. And so we should care about these black holes in their own rights as well. So it's important that we get a full picture of these black holes. And again, the main goal, kind of large, big picture goal here is to understand how black holes and galaxies co-evolve over time. And while we're getting pretty good at getting the underlying population at redshift 0 at today, the challenge is, and will continue to be, the population in the very early universe. That's very difficult to see, and that's exactly what LISA will help us better understand, the population of black holes, the underlying population of black holes at very early times. But one point, if you get anything out of this talk, is that in order to understand this in a theoretical level, you cannot divorce the evolution of black holes from the evolution of galaxies. If you want a model for the evolution of black holes, you need to include the evolution of galaxies, and vice versa. So in terms of this high redshift population, we've actually already made a ton of progress in the last year or so with JWST. The JWST has already begun to widen our view of the black hole populations at early times, getting to lower mass black holes and lower mass galaxies than ever before. Right? So we're expanding our view. Where we were at before JWST, we could only see the biggest, brightest, rarest things, but now we're starting to sample the underlying population, which is critically important. And this is what LISA will continue to do. This is one of the main things that people like me are excited about, getting at this population of low-mass black holes at early times, the seeds and building blocks to the more massive ones later on, and you see the synergy with the LISA kind of discovery space with all these different electromagnetic missions. Now, because, as I said, to understand black holes, you need to understand galaxies, one of the nicest tools to use to make predictions for massive black holes, to make predictions for LISA and what we'll learn, is cosmological simulations, specifically hydrodynamic simulations that self-consistently follow the evolution of galaxies with the large-scale environment, where every galaxy in these simulations has its own assembly history, its own environment, which shapes its internal structure, which shapes the growth history of their black holes. These can be very powerful tools to learn about the physical processes that are affecting black holes and galaxies at different times. The problem is that the way we model black holes in these simulations often makes a lot of assumptions that directly influences the results that we get out. And so in this talk in particular, I just want to highlight that we still don't know where black holes should exist. We don't know what galaxies should or shouldn't have them, when they should form, or what masses they should form at. We also often aren't able to fully resolve their dynamical evolution in galaxies, and so we have to make choices about when and where they should merge. And these two things in particular will shape a lot of the results I'll talk about. So I'm not saying you shouldn't believe anything, but what I will say is that pretty much every result from these simulations will be directly affected by these. So take that what you will. But we can still, by comparing results from different simulations and by looking at kind of general trends, we can still learn a lot about the processes that are important, and then use that to inform and learn from LISA in the future. So Melanie Habozit has done some great work collecting data from a bunch of different cosmological simulations, looking at how they're different, how they're similar. And so what I'm showing here is the black hole mass-stellar mass relation across different simulations. And all these simulations at high masses pretty much are the same. They all match the empirical relation that we see at low redshift, because they're tuned to do that, so it's not very surprising. What is interesting is that you can reproduce these observed empirical relations with any different physics model. These simulations have drastically different physics, and yet they're able to do the same thing. So, scaling relations are neat, but it doesn't really tell you much. What is interesting, though, is that all the simulations seem to predict rather mild evolution in this relation, and are very different at the low mass end. And this is the end that we should care about with LISA, because LISA will observe the lower mass black holes in lower mass galaxies. And this is where the simulations tend to disagree. And indeed, if you look at the overall distribution of where those black holes are in this black hole mass, stellar mass space, again, we see lots of differences at low masses, even though all these simulations are more or less able to get at the observed population in a broad sense. So they can all do the same thing pretty well with very different physics, but looking at the low mass end might tell us a bit about what's going on. So one other way that simulations do tend to agree with one another is the cosmic evolution of black hole growth over time. Right? Looking at the luminosity of black holes versus their mass in all these different simulations, even though there's differences in each of these in the details, everyone predicts that at earlier times, black holes are growing more rapidly, more high Eddington ratio growth. And as time goes on, black hole growth declines, especially at high masses, the cosmic downsizing, if you will, of black hole growth. And so, okay, they grow faster at early times. What's actually driving or regulating the growth of these black holes? And so for that, we can compare the accretion history of black holes in the universe to the star formation history of the universe. So this is a plot showing the accretion rate density of black holes in one color, in the red colors, and in blue, the star formation rate density of the universe. So black hole growth seems to follow star formation in the universe, and indeed, in simulations, we see this happen at a galaxy-to-galaxy scale. So looking at the black hole accretion rate versus star formation rate of individual galaxies in our simulations, we can see that they follow basically a constant relationship with redshift, that the more star formation that's happening, the more black hole growth is happening in a galaxy, and it's roughly consistent with the observed so-called AGN main sequence that we see. And so what this tells us is that black hole growth is primarily limited by essentially the gas supply. It's a supply-limited thing. The more gas there is, the more star formation there'll be, and the more black hole growth there'll be. And also, that black holes tend to grow continuously with their host galaxies along the scaling relations that we see. Now, interestingly, we find, and this is something more and more that's coming from simulations, is that the connection between mergers and black hole growth is very weak. We don't see any strong correlation between the Eddington fraction of a black hole's growth and a merger event occurring. Mergers do not drive long periods of high Eddington rate accretion. They do not grow mostly during merger events. Most of their accretion is happening continuously with the galaxy, not in strong bursts. So black holes grow continuously, so we'd expect them to grow along this relation. So again, what the heck is going on at low masses in these simulations? Why do we see such a difference in the way different simulations predict the growth of black holes at low masses? And so for that, we have to move away from black holes and think instead about supernova. So if black hole growth is limited by the amount of gas that you have available to you to grow, the thing that limits that in low-mass galaxies is supernova. So the image I'm showing there is hot supernova-driven outflows in a dwarf galaxy. You have a weak potential well. Those supernova explosions drastically influence the gas supply of the galaxy. And so in simulations, when you have strong supernova feedback, you limit the growth of black holes at early times until the galaxy is big enough that it can hold on to its mass more efficiently. Indeed, the result of this is that at early times, this is creating a drastically different population of black holes in these low-mass galaxies. Black holes are starting their life in these small galaxies, and their gas supply is regulated by supernova. When you have strong supernova feedback, all of your black holes at early times in galaxies below a few times 10 to the 9 solar masses are essentially stuck at their seed mass. They don't have the gas supply because their supernova explosions are limiting them entirely. Another thing that's important, in addition to supernova, is UV radiation. The UV radiation from other stars and other galaxies limits the gas supply in low-mass galaxies. It makes it harder for gas to cool in these galaxies and for these low potentials to hold on to their gas. And this is something, again, the dwarf galaxy community knows well, but this also influences the growth of black holes. Even in addition to the supernova-limited growth we see here, if you include UV, you have even smaller black holes at earlier times. And now, that's interesting, but it also poses an interesting problem because what JWST is observing are quite massive black holes in small galaxies. So how the heck do we get those? We've just said that it actually is pretty hard to grow black holes in small galaxies if you have supernova exploding all the time. Even if you have a relatively weak feedback, it can be difficult. So what's going on there? And the answer is mergers. So black holes go through mergers, and they dominate the growth of black holes at early times. So this is the work led by my master's student, Patrick Hedgel, looking at the fraction of mass gained through accretion as a function of host galaxy mass in Romulus. And so what we see here is that even at redshift 5, black holes have gone through several, even 10 mergers, and that merger growth is what dominates their overall mass. Even the most massive galaxies at early times, their growth is dominated from mergers, with only a very small number of exceptions. And this includes the black holes that are growing currently at a pretty high Eddington fraction. So even the black holes, the bright ones that we see, the majority of their mass comes from mergers, right? And so the knock-on effect here is that if we look at the most massive black holes in the most massive galaxies, that affects how we interpret their growth histories. This is work led by my student Lee Whitaker, who's a finishing undergrad, soon to be postgrad, working with me. And she's been looking at the ex situ fraction. So how much mass accretion from massive black holes comes from other black holes that merged with it rather than its own accretion history. And so for the most massive galaxies that host the most massive black holes with the most complex merger histories, a third or more of the mass that black hole has gained comes from its merger history. So mergers are crucial in growing black holes over cosmic time. And what that means is that we're now very sensitive to our models for how we seed black holes in our simulation, which I just said, very uncertain. And so recent work using the Brahma simulations showed that if you make seeds very common, you have a bunch of mergers, and you're able to grow black holes to quite high of mass rather early on, even reaching the masses that we observed with JWST. While if you have very rare seeds, you don't go through mergers, and you have lower mass. That might seem obvious, but that means is that the early growth of these black holes is basically completely tied to mergers, and therefore completely tied to seeding of the black holes in the simulations, which, like I said, very uncertain. But that also means that the merger rates, the rates that we'll detect with LISA, are not only measuring the population of black holes at early times, it's also a measure of the main growth channel of those black holes at early times, which is very interesting. So what can these simulations actually tell us about the merger history of the universe? And there is a bit more problematic, right? The merger history of these simulations, the merger rates as a function of redshift, shown on the left there, can vary dramatically from simulation to simulation because of these variations in physics and seed formation models. Now, the plot I'm showing here, it might actually seem not so bad, maybe only an order of magnitude difference, but it's actually much worse than that. If you were at Matteo Bonetti's talk yesterday, you know that we're working to collect a bunch of different simulation data together and semi-analytic models together. So the picture is actually significantly worse, several orders of magnitude differences between simulations. And things like seed models. On the right here, I'm showing different dynamical models. So whether or not you assume black holes merge instantaneously or whether or not you assume they model for dynamical friction on galaxy scales changes additionally, orders of magnitude difference in mergers. So you shouldn't believe any merger rates from simulations, but we can still learn some things looking at general trends in simulation data. And so one interesting thing that's come up using the Astrid simulations, which seed black holes at lower masses and in lower mass galaxies than other large-scale simulations, we find that the majority of mergers that would be detectable with LISA involve seed black holes. And not only seed black holes merging with other seeds, but seed black holes merging with quite massive galaxies, even 100 solar masses, 100 times the mass of those seeds or more. And if you look at massive black holes at redshift, 5, 4, 3, these massive black holes are going through mergers every gigayear or so, but the majority of those mergers are coming from seed black holes, coming in and merging with them. And some of those seeds have been in the galaxy for a really long time. In fact, so you should go check out Jillian Bellaveri's poster outside. It shows some other examples of this type of situation happening where you have a massive black hole that eventually merges with a low-mass black hole that might have been in the galaxy for billions of years. Right? So seeds are important to the merger stream, and mergers are important for the growth. But what do we also know about the time scale that these mergers are taking place? Right? As I said, these low-mass seeds have sometimes been in the galaxy for billions of years. And indeed, if we take simulations that attempt to model the dynamical evolution of these black holes over time, we find a very wide distribution of how long it takes black holes to actually reach the centers of galaxies after a galaxy merger. Sometimes these black holes can take billions of years sitting in the same galaxy before they reach the center of that galaxy and merge with the black hole. And so what causes this? It all has to do with the morphology of the galaxies causing the black hole merger. So this is an example of a quickly forming black hole merger in the Romulus simulations, and this is an example of a slow forming black hole merger. And the main difference between these is that at the top, you can see there's two different galaxies in all of these images, while on the bottom, the black hole is kind of by itself. And so what's happening here is when you have a galaxy merger that results in an early tidal disruption of the secondary galaxy, the black hole takes a really long time to get to the center. The main way that black holes get to the centers of galaxies is through galaxy interactions, not through dynamical friction on their own. So the galaxies need to bring the black holes together, and so that means that which mergers result in a faster, slow-forming black hole pair depends entirely on the mass ratio and the morphology of those galaxies. And so this has a few different knock-on effects. The fact that black holes can take a long time to reach the center. One thing that this causes is it becomes really difficult to pinpoint potential host galaxies for these binary black holes. Right? If you're looking for merger-like properties to the galaxy, you're not going to find that. Because in these simulations, for example, you can see when the galaxies merge, you can see when the black holes merge, what the galaxy looks like in the simulation, and then if you add additional time to account for binary evolution, what the galaxies look like. So these galaxies are not merging they're not obvious merger remnant galaxies. They're just normal everyday galaxies. And so it becomes trickier to pinpoint potential host galaxies, although I'll just quickly say that that's not necessarily impossible. We have some results showing that for massive mergers at low redshift, we might be able to tell the difference, but that's more related to pulsar timing. It remains to be seen whether or not this works at low masses and high redshift. But just wanted to quickly mention that. So it changes the morphology of the host galaxy. But it also means that many galaxy mergers will never result in the merger of two black holes. That two galaxies with black holes merge, and their black holes never reach the center, and so we have a population of wandering black holes. And this is a problem that people have been thinking about for a while now, but now we can actually begin to predict these in large-scale simulations. And so, Milky Way-like galaxies can have a few. Large, brightest cluster galaxies can have many hundreds or even thousands of these wandering black holes within them. So these represent a huge population of black holes that are very difficult to see, that have gone through their own growth and merger history previously, which again are important for understanding the overall population of black holes. And indeed, if we look at the accreted mass that these black holes have accumulated over time at different redshifts, that accreted mass versus halo mass, the black points on this plot represent central black holes, and the colored points represent these wandering black holes. So as you get to beyond redshift 2, the majority of the mass that has been accreted by black holes is in wandering black holes, off-center from their galaxies. Indeed, I have another student, Ben Sheehan, who's been working on this. He's another finishing undergrad who's going to be a postgrad working with me. If we look at the accretion rate density of the universe, this yellow line represents central black holes, which nicely actually matches the JWST constraints here, but that only represents about half of the accreted mass density in the universe. The rest is from off-center black holes at any given time. So these black holes are accreting. They represent an important distribution of masses in the universe. At redshift 0, they're dominating at low masses, below 10 to the 7. There's just a lot of these wandering black holes. They're contributing a lot to the population, and they're worth thinking about. So all of this that I've talked about, the dynamics of black holes, the supernova-regulated growth, the seed masses, how often and what mass you seed the black holes, all of these will have direct implications for what we think LISA will detect. So these are results from semi-analytic models that take into account different seed models, different dynamical models, and different supernova feedback models. All these lines basically represent the effects that all these things have. They're important for understanding the number of mergers, the mass distribution of those mergers, and the redshift distribution of those mergers. And so we'll be able to learn a lot from LISA because it'll be constraining to our models, and hopefully we'll be able to interpret using these simulations the data that we get from LISA, which is exciting. But now I want to use my last couple minutes here to talk about where we need to go with these large-scale simulations. Now that we have JWST flying, we're already learning about these low-mass black holes and low-mass galaxies, and we're seeing that simulations are incredibly limited to actually learn about these structures. If we care about the lowest mass things in the early times, none of these simulations are really well suited to study that, and we need to improve it. So the first thing is resolution. So I wanted to point out these nice results from Voluntari et al. 2020, showing that if I can take a big volume at low resolution and calculate the merger rate, and then I take the same model and apply it to a high-resolution simulation in a smaller volume, I get more mergers. Because as you go to higher resolution, you're resolving more galaxies, more structures, more mergers, and so you get more galaxy mergers, even without the seeding model being too different, right? And so resolution matters in an overall sense for merger rates, actually resolving the galaxies, but it also matters when it comes to star formation and supernova. The higher resolution your simulation, the better you can resolve dense, bursty star formation in galaxies, because you can form stars at higher densities. I know this isn't a star formation conference, but it matters. And that changes the nature of supernova so that you can then create cored dark matter profiles. It changes the nature of dark matter, which can then affect the formation and evolution of black holes. actually forming the binaries could become harder when you have a core dark matter profile. Where black holes are within galaxies can be different. All that matters a lot. And so I just wanted to end here by showing this is what a typical galaxy merger that would be a LISA observable object looks like in typical cosmological simulations. And that's pretty sad. This is what we're currently using to make predictions for LISA. And I'm trying to say, this is the environment that a black hole is evolving in. So what we really need to do is get to much better resolution. And we can do this right now at individual galaxy levels, and that's what we've been working on, really enhancing the resolution so we can actually see the environment that these black holes are evolving within. Allows us to look at the distribution of mass and dark matter, gas and stars nearby the black hole that's evolving as a binary. And importantly, will allow us to look at the morphology and kinematics around the black hole, all of which will help us determine the smaller scale evolution of those binaries, right? And so one thing we're seeing is chord profiles, which is pretty interesting. But really where we need to go are these high resolution simulations that can resolve these low mass galaxies, resolve the initial formation of black holes in these tiny structures in the early universe. There's a couple posters out there that are on this, so I think you should check those out as well. And I'll thank you for your time since I'm already a bit over. And I'll just have my conclusions up there and I'll take your questions.
Thanks, Michael, for this amazing overview. So we have a few questions. So over there, the first one, then Katie.
Thanks, that was a great talk. I have a possibly naive question from having LBK black holes on the brain, but I'm wondering how kicks from black hole mergers, especially in the lowest mass galaxies, might impact the rates and how those are accounted for in the cosmological simulations, or if they are. And I see your smile, and I fear I know the answer. Okay.
No, that's a great question. And that's another big limitation. So there are simulations that do attempt to track spin of the black holes. Not so many actually do the kicks. And again, most of these simulations wouldn't resolve the dynamics anyway, so if they did do kicks, it wouldn't matter because they'd be pushed back to the center automatically no matter what. And then if you do try to resolve the dynamics, you worry how well you're good at resolving those dynamics. At best you can tell in the big simulations, at best you could tell a black hole is more than a kiloparsec away from the center. So the detailed kinematics would be tricky. So I think we're moving to that point. I think as we get to high resolution, we can do a better job tracking the spins of black holes and the dynamics, and so maybe we can do better. I personally have been scared to put kicks because of the dynamics issues, and you worry about creating a population of off-center black holes and no central black holes, which would be hard for a really expensive simulation. But I think we're heading there, and I think we do need to take into account the kicks, and most simulations don't at the moment. And again, the ones that do don't really do the full job.
I'm over here. Oh, I have to get real close. You told me that. Thanks for an excellent talk. When you showed the interplay of star formation and supernovae with BBH mergers, of course, as a binary star person, what I immediately thought of was, are you incorporating binary interactions in your supernova feedback? And then you got to even higher resolution, which I think currently the simulations don't incorporate binaries, but as you go to higher resolution, is there a plan to consider the impact of binaries in terms of both delay times and runaway systems from, say, disrupted binaries?
I've had this conversation recently. We don't take into account delay times. Right now we have essentially rates of supernova as a function of age. We don't take into account binary evolution. That'd be really cool to look into. I don't know if this, maybe you could tell me that high resolution in this case is 10 to the 3 solar masses, mass particles for stars. So if you think it would matter there, then it's definitely worth thinking about for sure.
Yeah.
And people have brought that up to me before, so yeah. I will say there is some leeway. So this weak and strong feedback, there's not one that's necessarily more realistic than the other, because there is also some leeway in terms of the efficiency, the effective efficiency of feedback, which kind of all rolls that physics together.
So I have two questions or comments. So is it a fair characterization that Lisa's going to tell us at the end of the day, right? You're trying to pin down the key physics determining the wild range in these low mass mergers, but at the end of the day, we don't know what's right, and Lisa's going to tell us the answer. And the second question is, where are all the wandering black holes? Like what in M87? Where's the bunch of ones that didn't get tidally stripped? And I've done models where also all these stalled satellites, but where are they? Like, yeah.
So for the first question, I mean, yeah, man, Lisa's going to be great, obviously. So I think this is why, like, I think that there's a cyclical process here. Like these simulations, cosmological simulations, semi-analytic models will help us contextualize the LISA data and then put it in a way that will help us inform the models, and if so, like LISA data by itself, just going one direction, we need more information. What's the context? What mergers are happening? What phase of growth are we being subjected to? And that's what we can know from the simulations in general, even with their uncertainties. And so I do think with that cyclical process, we'll learn a lot from LISA, the mass distribution at a high redshift, the merger distribution at high redshift. In terms of the observing the seeds or the wanderers, I think that there is actually some interesting evidence in the form of hyperluminous X-ray sources. So we've looked at the spatial distribution that we predict in the simulations. They match quite well in terms of luminosity and spatial distribution to hyperluminous X-ray sources. And so I think that's an interesting candidate for these things. I will say, in general, they're not accreting very much, and so they'll be hard to see no matter what. But yeah, I think that we might be seeing them. It's just hard to interpret that, especially when we look for, you're either looking for X-ray emission from X-ray binaries or central AGN. So we haven't been searching as much for these luminous sources, and so I think there's some room there. There's also some interesting things with streams and breaks in the stream in the Milky Way, which are really interesting. I think there's some interesting ideas there in terms of black holes potentially affecting things dynamically, but I won't get too into that. Yeah.
Great talk, Michael. Oh, great talk, Michael. So I'm just wondering how good or bad is our present feedback model from AGN typically in these simulations?
Oh, from AGN.
Yeah.
I think pretty much yeah, I mean bad. I mean, in the sense of we just don't know. We don't know how feedback works. It creates lots of challenges because you can create simple models that are simple, meaning that they're nice and predictive. And you don't have to worry about too many constraints and turning too many knobs. But you're probably missing things like jets and things like that. And you have, when do you launch a jet? When do you not launch a jet? All that stuff is very complicated and depends on physics that are not resolved at all. And so, yeah, it's hard. We're getting there. My typical philosophy has been to try to do the simplest thing the best way possible and go from there. But I can understand other methodologies as well. But again, they all have consequences. So for example, when you make complex models deciding when and where to turn on jet feedback, that ends up having an influence on your results in a very real way, and you typically don't like that. I mean, we don't like it when the seeds matter for mergers. You don't like it when your feedback model's directly determining anything. So, yeah, it's tough.
Cool. Thanks.
Okay, the timer is blinking and it's lunchtime, so let's thank Michael again.